Something is wrong with our universe, not in a catastrophic way, not yet, anyway, but in a deeply puzzling one. Scientists have spent decades mapping the cosmos, measuring the light of distant galaxies, tracking the expansion of space itself. And yet, for all their calculations, there's a glaring discrepancy, a cosmic accounting error, if you will. The universe's energy budget doesn't add up. In fact, a staggering 2/3 of the energy that should be out there is missing, vanished, undetectable. Where did it go? Why can't we find it? And what does this mean for the fate of everything we know? This isn't just some abstract scientific quirk. It's one of the most profound mysteries in all of physics. Think of it like balancing a checkbook, only to realize someone has quietly siphoned off most of the money without leaving a trace. The numbers stare back at us, undeniable and unsettling. The visible universe, the stars, planets, and galaxies we can observe, makes up less than 5% of what should be there. The rest, a ghostly presence known as dark energy and dark matter, elusive forces that refuse to reveal themselves, yet dictate the very fate of the cosmos. So why should this matter to you? Because this missing energy isn't just a puzzle for astronomers, it's a question that strikes at the heart of reality itself. If we're wrong about the fundamental forces shaping the universe, what else might we have misunderstood? Could cracking this mystery rewrite the laws of physics? Today, we're diving deep into 30 of the most compelling theories about where that missing energy might be hiding, from hidden dimensions and cosmic shadows to the mind-bending possibility that we're not just missing something but misunderstanding everything. Buckle up, the answers, or lack thereof, might just leave you questioning the fabric of existence. Few ideas in physics have had a stranger journey than the cosmological constant. It all began with Albert Einstein himself, though at first he never intended it to explain missing energy. In fact, he introduced it for the opposite reason, to keep the universe still. Back in 1917, most scientists, including Einstein, believed the cosmos was eternal and unchanging. But his own equations of general relativity suggested something unsettling, that the universe should either be expanding or contracting. Unwilling to accept that, Einstein tweaked his math by adding a fudge factor, a repulsive force baked into space itself to counteract gravity's pull and preserve a static cosmos. He called it the cosmological constant. Then, in 1929, Edwin Hubble made a discovery that shattered that vision. Distant galaxies weren't just moving, they were racing away from us. The universe wasn't static at all, it was stretching, expanding in every direction. Einstein famously called his own cosmological constant his greatest blunder and discarded it. But here's the twist: decades later, that so-called blunder might be the very thing solving our missing energy problem. In the late 1990s, astronomers made another bombshell observation. Not only was the universe expanding, but the expansion was speeding up. Something was overpowering gravity, pushing galaxies apart faster and faster. That something, a mysterious, invisible force acting like, well, Einstein's old cosmological constant. Today, we call it dark energy, an energy woven into the fabric of space itself, driving the accelerated expansion. Here's where things get eerie. Measurements suggest dark energy makes up about 68% of the universe's total energy budget. That lines up suspiciously well with the missing energy we've been searching for. But what is it? If it's the cosmological constant resurrected, then it's a property of empty space, a sort of background energy that never dilutes, no matter how much the universe grows. Quantum physics even offers a possible explanation: fleeting particles popping in and out of existence in the vacuum, generating a tiny repulsive force at every point in space. Yet there's a catch. When scientists calculate how much energy these quantum fluctuations should produce, the numbers are staggeringly off by a factor of 1 followed by 120 zeros. That's the worst prediction in the history of physics, so either we're missing something fundamental about quantum theory, or the cosmological constant isn't the full story. But for now, it remains the leading explanation for dark energy, a ghostly presence first imagined by Einstein, then abandoned, and now haunting us as the universe's biggest accounting error. What if dark energy isn't a fixed feature of space, but something far more fluid, a cosmic chameleon that changes over time? That's the tantalizing premise behind quintessence, a theory that flips Einstein's static cosmological constant on its head. Unlike its rigid predecessor, quintessence proposes that dark energy is a dynamic field, one that ebbs and flows across the ages, potentially explaining why our universe's expansion rate doesn't quite add up. Imagine dark energy not as a steady hum in the background of space, but as a symphony with crescendos and silences, its intensity shifting as the cosmos evolves. This idea borrows from an ancient concept, the Greek word quintessence, once referred to a fifth element beyond earth, air, fire, and water, a pure substance making up the heavens. Today, it's been resurrected to describe a speculative energy field that permeates the universe, behaving more like a fluid than a constant. Here's where it gets revolutionary. While the cosmological constant suggests dark energy's density remains unchanged even as space expands, quintessence allows for a flexible energy density. It could have been stronger in the early universe, weaker during certain epochs, and might even flip from repulsive to attractive in the distant future. Why does this matter? Because observations of distant supernova and galaxy clusters hint that dark energy's influence hasn't always been uniform. Some measurements suggest the acceleration of the universe's expansion wasn't as pronounced billions of years ago as it is today, a wrinkle the cosmological constant struggles to explain. Quintessence, with its mutable nature, could account for these discrepancies. Picture it like a thermostat for the cosmos, subtly adjusting the strength of dark energy in response to changes in the universe's structure or size. But what would this field be made of? Theorists propose exotic particles or undiscovered forces, perhaps even relics from the inflationary period right after the Big Bang. Unlike the cosmological constant's bland uniformity, quintessence could interact with other forms of matter and energy in subtle ways, leaving fingerprints in the large-scale structure of galaxies or the cosmic microwave background. Some models even suggest it might eventually dissipate entirely, leading to a future where gravity regains dominance and the universe collapses in on itself, a dramatic twist the cosmological constant could never accommodate. Of course, quintessence isn't without its puzzles. If it's a dynamic field, why haven't we detected its fluctuations? Why does it seem so finely tuned to dominate the universe's energy budget now, at this precise moment in cosmic history? Skeptics argue it's a convenient placeholder, a way to patch over gaps in our understanding without concrete evidence. Yet for others, its flexibility is its strength, a framework adaptable enough to embrace new discoveries without crumbling. Whether quintessence is the missing piece of the cosmic puzzle or just another intriguing dead end, one thing's certain: it challenges us to rethink not just where the universe's energy is hiding, but how it might be transforming right under our noses. Phantom energy takes the mystery of dark energy and cranks it up to terrifying new heights. While ordinary dark energy pushes the universe to expand at an accelerating rate, phantom energy suggests something far more violent, a force that doesn't just expand space but amplifies itself over time, growing stronger as the universe stretches. The consequences: a cosmic doomsday scenario called the Big Rip, where every structure in existence, from galaxies to atoms, is torn apart in a final, cataclysmic instant. Here's how it works. In most models, dark energy maintains a constant density as the universe expands, meaning its repulsive effect stays steady, but phantom energy behaves differently. Its density increases as space grows, creating a runaway feedback loop. The more the universe expands, the more powerful phantom energy becomes, the more powerful it becomes, the faster expansion accelerates. It's like stepping on a gas pedal that sinks further the faster you go, until eventually you're hurtling toward oblivion with no way to stop. The math behind this is chilling. If phantom energy exists, the universe's expansion rate wouldn't just speed up, it would approach infinity in finite time. First, galaxy clusters would be ripped apart as the space between them stretches too violently for gravity to hold them together. Then, individual galaxies would unravel, solar systems would be shredded, planets would disintegrate. In the final moments, even atomic bonds would snap, reducing all matter to disconnected particles drifting in a vast, empty void. What makes this idea especially haunting is the timescale. Some calculations suggest the Big Rip could happen in as little as 20 billion years, a blink of an eye on cosmic scales. But here's the twist: phantom energy isn't just about destruction. Its existence would force us to rewrite our understanding of fundamental physics. Most forms of energy obey what's called the null energy condition, a rule that prevents certain bizarre behaviors in spacetime. Phantom energy violates this, implying that the universe might allow phenomena we currently consider impossible, like time-reversed effects or wormholes. Could such an extreme form of dark energy really exist? Observations so far are inconclusive, but some measurements of the universe's expansion rate show slight deviations from what the cosmological constant predicts, just enough to leave the door open for phantom energy's nightmare scenario. Whether it's out there or not, the mere possibility challenges our assumptions about the universe's fate and reminds us just how little we truly understand about the forces shaping reality. One thing's certain: if phantom energy is real, the cosmos isn't just expanding, it's on a collision course with its own annihilation. What if the universe's missing energy isn't missing at all? What if we've simply been reading gravity's rulebook wrong? That's the radical proposition behind modified Newtonian dynamics, or MND, a theory that tosses dark energy aside and rewrites the laws of gravity themselves. Instead of invoking some invisible force to explain the universe's accelerated expansion, MND suggests we're witnessing the limitations of Newton's centuries-old equations playing out on cosmic scales. It's not that the energy is missing, it's that our math has been incomplete all along. The story begins with galaxies behaving badly. In the 1930s, astronomers noticed something odd about how stars orbit the centers of galaxies. According to Newton's laws, stars on the outer edges should move slower than those near the center, just like planets farther from the sun take longer to complete their orbits. But observations revealed the opposite. Outer stars raced just as fast as inner ones, as if some unseen mass were tugging on them. This anomaly birthed the idea of dark matter, an invisible substance providing the extra gravitational glue. MND offers a different explanation, proposed by physicist Mordechai Milgrom in the 1980s. It suggests that gravity doesn't weaken as quickly over large distances as Newton or Einstein predicted. Below a certain acceleration threshold, a tiny but critical value gravity's pull transitions to a gentler decline. This subtle tweak to the math perfectly reproduces the flat rotation curves of galaxies without needing dark matter's phantom mass. And if it works for galaxies, could it also explain the universe's accelerating expansion without dark energy? Proponents argue yes. They point out that cosmic acceleration might not require a mysterious repulsive force, just a correction to how gravity behaves in the vast, sparse regions between galaxy clusters. In this view, the apparent push driving galaxies apart is actually gravity's long-distance weakness, making the universe's expansion appear to speed up when measured with our current flawed equations. It's like realizing you've been mistaking a dimmer switch for an on-off button. The light wasn't getting brighter, you just didn't understand how the controls worked. But MND isn't without controversy. While it excels at explaining galaxy rotations, it struggles with other observations, like the gravitational lensing effects around massive galaxy clusters, which seem to require unseen mass. Critics also note it lacks the elegant universality of Einstein's relativity, requiring ad hoc adjustments for different scales, yet its persistence as an alternative underscores a deeper truth. Our gravitational models, for all their precision, are still approximations of a cosmos that constantly surprises us. Whether man ultimately succeeds or fails, it reminds us that the universe's greatest mysteries might not lie in what we've yet to discover, but in what we thought we already knew. Quantum fields whisper to us from the vacuum of space, not in words, but in numbers so colossal they defy comprehension. According to quantum field theory, empty space is anything but empty. It seethes with fleeting particles and antiparticles constantly blinking in and out of existence, a quantum froth that should, in theory, generate an unimaginable amount of energy. This is vacuum energy, a concept that should be the crown jewel of physics, uniting quantum mechanics and cosmology. Instead, it's become the discipline's most glaring embarrassment. Here's the problem. When physicists calculate how much energy these quantum fluctuations should produce, the numbers are absurdly large, round 1 followed by 120 zeros times stronger than the dark energy we actually observe. To put that in perspective, it's like predicting a single ripple in a pond should unleash the power of a million tsunamis. This discrepancy isn't just a minor hiccup. It's the largest mismatch between theory and observation in the history of science. Nobel laureate Steven Weinberg dubbed it the worst prediction ever made. So where's the disconnect? One possibility is that our math is missing a crucial cancellation mechanism, some symmetry or unknown physics that almost entirely negates vacuum energy's expected strength, leaving behind only the faint ghost we call dark energy. Imagine balancing a mountain on the head of a pin, only for some unseen hand to shave off 99.999% of its mass without explanation. That's the level of fine-tuning required to align theory with reality, a coincidence so precise it strains credulity. Another angle suggests we're misunderstanding vacuum energy entirely. Perhaps particles popping in and out of existence don't contribute to gravity the way we assume. Some theorists propose that these fleeting quantum events might cancel out gravitationally, like waves crashing together to leave calm water. Others argue that vacuum energy does exist at full strength, but most of it's locked away in extra dimensions or hidden sectors of reality, leaking only traces into our observable universe. The stakes couldn't be higher. If vacuum energy really is the source of dark energy, then solving this puzzle would reveal a profound link between the quantum realm and the cosmos's fate. But until we reconcile these impossible numbers, the vacuum remains both the most promising and most humbling frontier in physics, a reminder that space, even at its emptiest, holds secrets we're only beginning to glimpse. What if the universe's missing energy isn't lost, just hidden in plain sight, encoded on a cosmic boundary we can't see? That's the mind-bending premise of the holographic principle, a theory suggesting our three-dimensional reality might be nothing more than a projection, like a movie playing on the surface of an unimaginably vast sphere. According to this idea, all the information, and by extension all the energy, we perceive in the universe could actually reside on a two-dimensional surface at its edge, making our experience of depth and volume an elaborate illusion. This isn't science fiction. It stems from cutting-edge work in black hole physics, where scientists discovered something startling. The maximum entropy or disorder a region of space can contain doesn't scale with its volume as you'd expect, but with its surface area. It's as if the universe has a built-in limit on how much information can exist inside a given space, as though everything within is somehow written on its outer shell. This bizarre property mirrors how holograms work, where a 3D image emerges from flat, etched plastic when hit with light. If the cosmos operates similarly, then the energy we've been struggling to account for might simply be smudged across this hidden boundary, redistributed in ways our 3D-centric math fails to capture. How would this solve the missing energy problem? Imagine trying to tally the electricity usage of a city by only counting the power flowing through visible wires while ignoring the wireless signals humming invisibly around you. Our current energy calculations might be making the same mistake, assuming everything must reside within the space we can see, rather than recognizing it could be stored on a distant, unseen surface. The holographic principle redefines where energy lives, suggesting the discrepancy vanishes if we stop expecting it to fit neatly inside the volume of the universe and instead recognize it's been etched onto the cosmic perimeter all along. But here's where it gets even stranger. If the holographic principle is correct, it implies a radical rethinking of spacetime itself. Just as a pixelated screen can still display a smooth image, our seamless experience of reality might emerge from discrete bits of information packed onto the universe's edge. Energy wouldn't be missing, it would just be structured in a way that's fundamentally foreign to our intuition. This could explain why dark energy seems so evenly spread and weakly interacting. It's not a substance within space, but a feature of the framework projecting space. Skeptics argue this is speculative, and they're not wrong. No direct evidence yet proves our universe is holographic. But the math is compelling, and it offers something rare in cosmology, a way to reconcile the infinity-sized problems of quantum vacuum energy with the finite, observable effects we measure. Whether the holographic principle holds up or not, it forces us to confront an unsettling possibility. The energy we've been hunting for might not be lurking in the shadows of our universe. It might be staring back at us from the edges of reality itself. What if dark matter and dark energy aren't separate entities at all, but different faces of a single, shadowy substance that permeates the cosmos? That's the bold claim of dark fluid theory, a model proposing that the universe's two greatest mysteries might stem from one unified cosmic ether with bizarre, shape-shifting properties. Imagine a Chaplyginic medium that acts like invisible matter within galaxies, clumping and pulling with gravity's grip, yet morphs into a repulsive force in the vast voids between them, pushing space apart. This dual behavior could explain both the missing mass binding galaxies together and the unseen energy driving cosmic acceleration, all within a single framework. The secret lies in dark fluid's pressure, or more precisely, how that pressure changes depending on its environment. In dense regions like galaxy clusters, the fluid would exert negative pressure, behaving like a sticky gravitational glue that holds stars in orbit. But in the near-empty expanses between galaxies, its pressure flips, becoming positive and acting as an anti-gravity force that stretches spacetime itself. This adaptability mirrors how water can flow like a liquid yet freeze into a solid under different conditions, except dark fluid's transformations are governed by the density of space around it. Why consider such an exotic idea? Because it solves two puzzles with one elegant twist. Observations show dark matter's effects dominating within galaxies, while dark energy's influence only becomes obvious at cosmological scales. Current models treat these as separate components, requiring fine-tuned ratios to match what we see. Dark fluid eliminates that need by suggesting we're observing different states of the same underlying substance. Think of it like steam and ice. Both are just H2O in different forms, yet their behaviors seem worlds apart. Critics argue the theory stretches plausibility, demanding a substance with properties never observed in any known matter or energy. But supporters counter that dark fluid's flexibility might explain anomalies like the bullet cluster, where colliding galaxies appear to separate from their dark matter halos, a phenomenon easier to reconcile if dark matter isn't purely particulate, but a dynamic medium responding to collisions in unexpected ways. Future telescopes mapping the universe's large-scale structure could hunt for telltale signs of this fluid's transition zones, regions where its gravitational pull subtly shifts to a repulsive push. Whether dark fluid ultimately holds up or not, it challenges us to think beyond the dichotomy of dark matter versus dark energy. Sometimes the universe's greatest secrets aren't hidden in separate corners, but woven together in ways we're only beginning to untangle. The universe loves a good shapeshifter, and Chaplygin gas might be its ultimate cosmic impersonator. Named after a Russian physicist from the early 20th century, this hypothetical substance starts its life behaving like dark matter, cold, clumpy, and gravitationally attractive, only to later transform into something resembling dark energy, pushing the universe apart with relentless repulsion. It's as if the cosmos hired a single actor to play both the villain and the hero in its grand saga, switching roles as the plot demands. What makes Chaplygin gas so intriguing is its equation of state, a mathematical description of how its pressure responds to changes in density. Unlike ordinary matter or even dark energy, Chaplygin gas follows an inverse relationship. As its density decreases, its pressure doesn't drop, it becomes more negative. Picture squeezing a balloon that resists harder the less air it contains. In the early universe, when matter was densely packed, this gas would have acted like a cold, sluggish fluid, clustering around galaxies and providing the gravitational scaffolding for cosmic structure. But as expansion thinned it out, its negative pressure would ramp up, morphing it into a smooth, repulsive force driving acceleration. The elegance of this idea lies in its economy. Instead of requiring two separate, mysterious components to explain dark matter's pull and dark energy's push, Chaplygin gas offers a unified solution. Early on, it mimics the gravitational effects of dark matter, explaining why galaxies rotate faster than visible mass alone can account for. Later, as the universe stretches and the gas dilutes, it transitions seamlessly into a dark energy-like phase, matching the observed acceleration of cosmic expansion. It's like discovering that the butler and the detective in a mystery novel are the same person, revealing a hidden unity beneath apparent duality. But no theory is without its ghost. Critics point out that Chaplygin gas struggles to explain certain observations, like the precise distribution of galaxies in large-scale surveys or the way dark matter seems to lag behind visible matter in colliding galaxy clusters. Some modified versions of the theory, like the generalized Chaplygin gas, tweak the equation of state to better fit data, but even these introduce new complexities. There's also the philosophical unease of replacing two unknowns with one mega unknown, a substance whose behavior defies all familiar physics, yet the allure remains. If Chaplygin gas exists, it would mean the universe's missing energy isn't just hidden, it's been masquerading as two different entities all along, evolving alongside cosmic history itself. Whether this shapeshifter stands up to future tests or fades into the annals of intriguing but flawed ideas, it reminds us that the cosmos might prefer elegant unity over messy multiplicity. And that, in itself, is a clue worth chasing. What if gravity isn't a fundamental force at all, but more like a cosmic illusion, a side effect of the universe's relentless drive toward disorder? That's the provocative idea behind entropic gravity, a theory that reimagines one of nature's most familiar forces as something far stranger, an emergent phenomenon bubbling up from the chaos of microscopic interactions. Proposed by physicist Eric Verland in 2010, this framework suggests gravity doesn't exist in the traditional sense. Instead, what we perceive as gravity might just be spacetime's way of balancing the books on entropy, the measure of disorder in a system. At its core, entropic gravity draws inspiration from a surprising source: thermodynamics, the study of heat and energy flow. Think of it like this: when you place a warm cup of coffee in a cool room, heat naturally flows from the coffee to the air until temperatures equalize. No mysterious force pushes the heat around, it's just the system seeking equilibrium. Verland's theory applies a similar logic to gravity, proposing that what we call gravitational attraction is really just spacetime's tendency to maximize entropy on microscopic scales. Massive objects like stars or galaxies don't pull on their neighbors through some invisible force. They gently nudge the surrounding space into a state of higher disorder, and other objects simply follow the gradient like marbles rolling down a slope. Here's where it gets revolutionary. If gravity emerges from entropy rather than being a fundamental force, the need for dark energy might vanish entirely. The accelerated expansion of the universe, typically attributed to dark energy's repulsive push, could instead reflect deeper, entropy-driven adjustments in spacetime's fabric. Picture a stretched rubber sheet that doesn't just sag under weight but actively reconfigures its microscopic structure to distribute strain. In this view, the universe isn't speeding apart because of some mysterious energy. It's spacetime itself evolving to maintain a kind of cosmic equilibrium we're only beginning to decode. The implications are staggering. Entropic gravity could explain galactic rotation curves without invoking dark matter, as the entropy gradients around galaxies would naturally produce the extra pull we attribute to invisible mass. It also offers an elegant solution to the cosmological constant problem, that infamous 120 orders of magnitude mismatch in vacuum energy. If gravity isn't a force in the traditional sense, then perhaps our calculations about how energy curves spacetime have been backward all along, but challenges remain. Critics argue entropic gravity struggles to explain phenomena like gravitational lensing or the precise timing of neutron-star mergers, where general relativity's predictions have been exquisitely confirmed. Others question whether entropy gradients could really produce effects strong enough to mimic dark energy's pervasive influence. Yet Verland's idea has sparked a vibrant debate, pushing physicists to reconsider whether gravity might be less like a cosmic rule and more like a cosmic habit, a pattern emerging from deeper, more fundamental principles. Whether entropic gravity ultimately holds up or not, it reminds us that sometimes the most profound insights come not from adding new layers to reality, but from questioning the very foundations we took for granted. Imagine our universe as a soap bubble floating in a vast, unseen ocean, a fragile membrane adrift in higher dimensions we can't perceive. This is the essence of brane cosmology, a theory that redefines reality by proposing our entire cosmos is just one three-dimensional brane existing within a higher dimensional space called the bulk. According to this radical framework, the energy we've been missing might not be lost at all. It could be leaking into these hidden dimensions or even transferring between colliding branes in ways that defy our everyday intuition. The roots of this idea stretch back to string theory, which suggests the fundamental particles we know might actually be tiny vibrating strings existing in 10 or 11 dimensions. Brane cosmology takes this further, painting our universe as a membrane of brane, where all known matter and forces are trapped like ink confined to the surface of a page. Gravity, however, could be different. Unlike other forces, it might seep into the bulk, weakening as it spreads across higher dimensions. This could explain why gravity feels so feeble compared to other forces, and why our measurements of the universe's total energy keep coming up short. Now, here's where it gets wild. If other branes exist parallel to ours in the bulk, their gravitational influence might subtly tug on our universe, creating effects we misinterpret as dark energy. Picture two bedsheets hanging side by side in a breeze. Even without touching, their ripples could interact. Some models suggest that a nearby brane passing through the bulk might exert a repulsive force on ours, steadily pushing space apart and mimicking dark energy's accelerating expansion. Alternatively, energy could be literally dripping off our brane into the bulk like water escaping a cracked cup, leaving us with a universe that seems to be missing a huge portion of its expected energy. There's a dramatic version of this scenario too, the ekpyrotic model, which proposes that the Big Bang itself wasn't a singular explosion, but the aftermath of two branes colliding in the higher dimensional void. In this view, the universe cycles through endless collisions, each one resetting cosmic history. The energy released during these crashes could explain not just dark energy, but the very structure of spacetime we see today. It's a cosmic reset button pressed over and over, with each collision redistributing energy in ways that leave our three-dimensional slice of reality perpetually unbalanced. Of course, brane cosmology isn't without its skeptics. If extra dimensions exist, why don't we see direct evidence of them? Proponents argue that these dimensions could be compactified, curled up so tightly that only gravity's whisper reaches us. Others point to tantalizing hints, like anomalies in high-energy particle collisions or subtle deviations in gravitational wave patterns that might one day betray the bulk's existence. Until then, brane cosmology remains a breathtaking what-if, a reminder that the answers to our universe's greatest mysteries might not lie within the confines of our familiar three dimensions, but just beyond them, in realms we're only beginning to theorize. Some of science's greatest discoveries began by questioning the unshakable, and few things seem more unshakable than the speed of light. For over a century, physics has treated this cosmic speed limit as an inviolable constant, 299,792 kilometers per second, no matter where or when you measure it. But what if we've been wrong? What if the speed of light isn't fixed after all, but has been slowing down over billions of years? This radical idea, known as variable speed of light theory, doesn't just rewrite the rules, it could unravel the mystery of dark energy by revealing that our cosmic measuring tape has been stretching all along. Here's how this audacious rethink changes everything. When astronomers measure distances to faraway galaxies, they rely on the assumption that light speed remains constant across space and time. If light actually traveled faster in the early universe, calculations based on today's speed would systematically overestimate how distant those galaxies are, creating the illusion that space is expanding faster than it really is. Imagine a mapmaker using an elastic ruler that subtly shrinks over decades. Later generations would conclude lands were drifting apart when in reality, the tool itself had changed. This faster light scenario could mimic dark energy's apparent accelerating expansion without requiring any mysterious repulsive force at all. Supporters of this theory point to tantalizing clues. Certain observations of quasars' extremely bright galactic cores show light spectra with subtle anomalies that some interpret as evidence of shifting light speed over cosmic history. There's also a profound mathematical elegance to the idea. If light speed was higher in the universe's hotter, denser youth, it could resolve lingering tensions in measurements of the Hubble constant, the value describing how fast the cosmos expands. Different measurement techniques currently yield slightly conflicting results, a discrepancy that might vanish if light's speed isn't the anchor we thought it was. Yet challenges loom large. Altering light's constancy sends shockwaves through physics, threatening to upend relativity's foundational equations where the speed of light isn't just a number, it's the fundamental conversion factor between space and time. Critics argue that even a tiny variation would destabilize the delicate balance holding atoms together or distort the cosmic microwave background beyond recognition. Worse, most variable speed of light models struggle to explain why other fundamental constants like the charge of an electron or Planck's constant wouldn't change in lockstep, which we've seen no evidence for. Still, the theory persists as a provocative alternative precisely because it forces us to confront our assumptions. After all, science once assumed the universe was static until Hubble proved otherwise. Maybe dark energy is another illusion, a cosmic mirage created by our stubborn belief that today's constants have always been. Whether variable light speed ultimately holds up or not, it serves as a vital reminder. Sometimes the most revolutionary answers don't come from inventing new forces, but from daring to re-examine the truths we never thought to question. What if the universe's rulebook isn't written in permanent ink? Most of physics rests on the assumption that fundamental constants, those unchanging numbers governing gravity, light, and quantum behavior, are truly constant. But lurking in the shadows of cosmology is a radical alternative. What if these immutable values are actually cosmic drifters, subtly shifting over billions of years? This isn't just about tweaking a few equations. If constants like Planck's quantum value or Newton's gravitational strength have changed over time, it could rewrite our entire understanding of the universe's missing energy problem, not by locating hidden forces, but by revealing that our measurements have been distorted all along. Take gravity's strength as an example. Newton's gravitational constant G determines how strongly masses attract one another across space. If G was slightly stronger in the early universe, the gravitational pull between galaxies would have been more intense in cosmic youth, potentially explaining why current expansion rates don't match predictions without invoking dark energy. Picture spinning a ball on a string. If the string gradually weakens over time, the ball's motion would accelerate even without any extra pushes. Similarly, a universe where gravity's grip weakens as it ages could mimic dark energy's apparent acceleration purely through changing constants. The same logic applies to Planck's constant, the fundamental number governing quantum mechanics. This value sets the scale for how particles interact with light and energy. If Planck's constant was smaller in the past, the energy density of the quantum vacuum, that seething sea of particle-antiparticle pairs, would have been vastly different across cosmic history. Suddenly, the infamous vacuum energy miscalculation, that one followed by 120 zeros discrepancy, might not be an error at all, but a snapshot of a constant caught mid-drift. Some models even suggest these shifts could be cyclical, with constants oscillating over trillion-year spans, resetting the universe's energy budget with each swing. Evidence for this provocative idea comes from unexpected corners of astronomy. Observations of distant quasars show light absorbed by ancient gas clouds in patterns that subtly differ from modern atomic physics, potential fingerprints of a different Planck's constant billions of years ago. Meanwhile, precision measurements of the cosmic microwave background reveal temperature fluctuations that some theorists argue align better with slowly varying constants than with standard cosmology. Even the Oklo natural nuclear reactor, a 2-billion-year-old uranium deposit in Africa that once sustained slow fission, hints at potential changes in the strength of fundamental forces, as its decay products appear slightly off from what today's physics predicts. Detractors counter that altering constants would unravel the universe's delicate fine-tuning. Stars rely on exquisitely balanced nuclear interactions. Even a few % shift in constants could render stellar fusion impossible or destabilize atoms themselves. Yet proponents argue that if multiple constants shift in tandem, gravity weakening while electromagnetism strengthens, the net effect might preserve life-friendly conditions while still explaining dark energy. It's a cosmic high-wire act where every adjustment demands compensating changes elsewhere. Whether time-varying constants hold up or not, they challenge a foundational assumption that the laws we measure today have always governed reality. Perhaps the missing energy isn't lost or hidden. We're just reading yesterday's physics with today's rulers, unaware that the markings on the scale have been fading all along. The Big Bang wasn't the universe's first act, it was the encore. According to cosmic inflation theory, an unimaginably brief but explosive period of expansion stretched the infant cosmos from smaller than an atom to the size of a grapefruit in a fraction of a second. This inflationary surge was powered by a mysterious energy field that temporarily dominated the universe, stretching space itself faster than light could chase it. Then, just as suddenly, the field decayed, dumping its energy into the hot soup of particles we recognize as the Big Bang. But what if it didn't all decay? What if traces of that primordial field still linger today, subtly tugging at the fabric of reality? That's the tantalizing possibility behind cosmic inflation residuals. The idea that dark energy might be the faint afterglow of the universe's explosive birth. Think of it like a campfire dying down. Even after the flames vanish, embers remain, radiating heat long into the night. Inflation's energy field could have left similar remnants, not enough to trigger another runaway expansion, but sufficient to gently push space apart at the accelerating rate we now observe. These residuals wouldn't behave like ordinary matter or radiation. Instead, they'd permeate the vacuum of space itself, a relic of that fleeting epoch when the cosmos rewrote its own rules. The math even hints at why this energy would be so weak today. As the universe expanded, the residual field's density would have diluted but not to zero. Like a whisper fading but never fully disappearing, it could persist as the faint, uniform pressure we call dark energy. Here's where it gets even more intriguing. Inflation wasn't perfectly uniform. Tiny quantum fluctuations in the early field left wrinkles in spacetime that eventually grew into galaxies and galaxy clusters. If inflation's energy didn't fully dissipate, those same imperfections might have left pockets where the residual field is slightly stronger or weaker. Some theorists suggest this could explain why dark energy's effect seems so consistent across the cosmos. It's not a new force, but the ghost of an old one, imprinted across space during those first chaotic moments. Not everyone's convinced. Critics point out that inflation's energy field was likely many orders of magnitude stronger than what dark energy appears to be. Bridging that gap requires delicate fine-tuning, almost as if the universe intentionally left behind just the right amount of residue to accelerate expansion billions of years later. Still, the elegance is undeniable. Rather than inventing a brand new dark energy, this theory ties two cosmic mysteries together: the universe's explosive beginning and its enigmatic present. Whether it holds up or not, the possibility reminds us that the answers we seek might not lie in what's been added to the universe, but in what's been left behind. Black holes aren't just cosmic vacuum cleaners, they're shredders, tearing apart the very information that falls into them. At least that's what Stephen Hawking once thought. His groundbreaking work on Hawking radiation revealed something startling. Black holes might slowly evaporate, leaving behind no trace of what they'd swallowed. This created the infamous black hole information paradox, a puzzle threatening the foundation of quantum mechanics, which states information can never be truly destroyed. But hidden within this paradox could lie clues to the universe's missing energy, tangled in the quantum chaos at the edge of oblivion. Here's how the pieces connect. Hawking radiation emerges from quantum fluctuations near a black hole's event horizon, where particle-antiparticle pairs constantly blink into existence. Normally, these pairs annihilate instantly, but at the horizon's edge, one particle can fall in while the other escapes, stealing a tiny bit of the black hole's mass in the process. Over eons, this drip-fed radiation would cause the black hole to vanish entirely. The problem: quantum mechanics insists the information about what fell into the black hole, every atom, every photon, must somehow survive, but Hawking's math suggested it was irretrievably scrambled. If information truly vanishes, it violates one of physics' core tenets, energy conservation. You can't destroy energy, you can only transform it. This raises a tantalizing possibility. What if the lost information isn't lost at all, but encoded in ways we're only beginning to grasp? Some theorists propose the missing energy might be trapped in the quantum foam, a seething, fractal spacetime at the smallest scales, where black holes churn information into a sort of cosmic cryptographic puzzle. Others speculate about white holes, the hypothetical opposites of black holes, where matter and energy erupt outward. If black holes funnel information and energy into these hidden channels, the universe's energy budget might balance after all, just not in any place or form we can currently observe. The implications ripple outward. If information isn't destroyed but transmuted, the energy it carries must go somewhere. Imagine throwing a book into a fire. The pages burn, but the atoms rearrange into smoke and ash. The information of the book still exists, just in a form you can't read. Black holes might be doing something similar, repackaging the energy of swallowed stars into Hawking radiation or ejecting it through quantum tunnels we can't yet detect. The catch: this process could be leaking energy into dimensions or timelines beyond our perception, creating the illusion of a deficit in our cosmic accounting. Recent breakthroughs add fuel to the fire. The holographic principle suggests all information falling into a black hole gets smeared across its event horizon like a celestial hard drive, preserving it in 2D form. Meanwhile, string theory's idea of fuzzballs, black holes as tangled knots of cosmic strings, hints at structures complex enough to stash missing energy without violating quantum rules. Even Hawking himself revised his stance before his passing, conceding information might escape after all, though how remains hotly debated. Skeptics argue these are elegant mathematical band-aids, not yet grounded in observable reality. But if even one of these theories holds water, the black hole information paradox could do more than resolve a quantum conundrum. It might unveil where the universe has been hiding its energy all along. The answer could be lurking not in the voids between galaxies, but in the last whispers of dying black holes, whispering secrets we're just learning to hear. Quantum entanglement is often described as physics' ultimate magic trick: particles separated by vast distances influencing each other instantly, as if space and time don't apply to them. But what if this bizarre phenomenon isn't just a quantum quirk? What if it's quietly fueling the universe's expansion itself? This is the jaw-dropping premise behind quantum entanglement energy, a theory suggesting that the cosmos's missing energy might not be missing at all. It's been hiding in plain sight, woven into the invisible threads connecting every particle in existence. At the heart of this idea lies one of entanglement's strangest features. When two particles become entangled, they share a single quantum state, no matter how far apart they drift. Measure one and its partner instantly knows, snapping into a corresponding state faster than light could travel between them. Einstein famously dismissed this as spooky action at a distance, but today we know entanglement is real, and it might be doing more than just linking particles. Some physicists propose that entangled pairs stretching across cosmic voids could generate minuscule repulsive forces, like invisible springs trying to pull space apart. Individually, these forces would be imperceptibly weak, but scale them up to the universe's vast web of entangled particles, and they could collectively mimic dark energy's gentle push. Here's why this isn't as far-fetched as it sounds. Quantum fields permeate every cubic centimeter of the universe, even in so-called empty space. These fields constantly produce entangled particle pairs that flicker in and out of existence. Normally, their effects cancel out, but in the gaps between galaxies where matter is sparse, the cumulative tug of countless entangled pairs might tip the balance. Picture two dancers holding hands while spinning apart. Their connection resists separation, creating tension. Now imagine trillions of such pairs spanning the cosmos, their combined resistance stretching spacetime itself. Critics argue that entanglement's fragility makes this unlikely. Most entangled particles decohere the moment they interact with their environment, snapping their mystical links. But supporters counter that certain exotic states, like topological quantum fields, could preserve entanglement across cosmic distances. Others point to the holographic principle, where entanglement entropy, a measure of quantum connections, appears to scale with the surface area of space, not its volume, eerily mirroring dark energy's uniform distribution. The most mind-bending implication: if entanglement drives cosmic acceleration, then the universe's expansion isn't powered by some external force. It's an emergent property of the quantum bonds stitching reality together. Dark energy wouldn't be a thing at all, but the side effect of spacetime's innate interconnectedness. Like realizing the wind you've been chasing is just the collective breath of every living thing on Earth. This theory reframes the hunt for missing energy not as a search for something lost, but as a failure to recognize what was always there. Of course, proving it won't be easy. Detecting entanglement's gravitational footprint would require instruments sensitive enough to measure the faintest whispers of quantum noise across light years. Yet the mere possibility shifts the conversation in a profound way, suggesting that the universe's greatest mystery might not be about what's absent, but about how deeply everything is connected. Picture a substance that doesn't just resist gravity, it actively runs from it, repelled by the very force that pulls ordinary matter together. This isn't science fiction. It's the startling premise behind negative mass particles, a hypothetical form of matter that could rewrite the rules of cosmic expansion. Unlike everything we've ever observed, these particles wouldn't fall toward massive objects like stars or planets. They'd flee, as if gravity had suddenly become a repellent rather than an attractor. If such exotic matter exists, it wouldn't just fill the universe's energy gap. It could single-handedly explain why space is stretching apart at an accelerating rate, all without invoking dark energy's mysterious push. The math behind negative mass is deceptively simple. Newton's second law states that force equals mass times acceleration, but if mass were negative, the equation flips. Applying a force would cause the object to accelerate in the opposite direction. Throw a negative mass baseball and it would curve backward toward your hand instead of arcing forward. Place it near Earth and it would shoot skyward, defying gravity's pull. Now scale this up to cosmic proportions. A universe sprinkled with negative mass particles wouldn't just hover passively. It would actively push itself apart as every particle's anti-gravity effect amplified its neighbors. The result, an accelerating expansion indistinguishable from dark energy's influence, but with a tantalizing twist. No unseen energy field required. Critics are quick to point out the paradoxes. Negative mass would violate the energy conditions that underpin general relativity, potentially allowing for impossible phenomena like perpetual motion machines or time-reversed causality. Yet supporters counter that the universe has surprised us before. Dark matter and dark energy were once considered heretical ideas too. Some theories even suggest negative mass could stabilize wormholes or explain the uniformity of the cosmic microwave background, offering solutions to puzzles beyond just missing energy. The most compelling version of this idea comes from the dark fluid hypothesis, where negative mass particles don't just repel ordinary matter, they repel each other, creating a self-reinforcing push that grows stronger as space expands. Picture a crowd where every person steps backward when someone approaches, causing the group to scatter faster the more they try to disperse. In cosmic terms, this fluid's density would remain constant as the universe grew, its repulsive force never diluting, exactly as dark energy appears to behave. But how could such bizarre matter exist? Quantum field theory allows for states with negative energy density under specific conditions, like the Casimir effect, where closely spaced metal plates create a region of negative pressure. Some speculate that exotic phases of quantum vacuum could spontaneously generate negative mass particles, or that they're remnants from the universe's birth, frozen into an unnatural state during inflation. Others propose they're not particles at all, but topological defects in spacetime knots or wrinkles left over from the Big Bang that just happen to behave like anti-gravity. Observational tests remain elusive but not impossible. If negative mass clusters differently than dark energy, subtle variations in the large-scale distribution of galaxies might betray its presence. Others hunt for anti-lensing effects, where negative mass bends light away from itself rather than toward it, creating telltale voids in gravitational lensing maps. The true challenge lies in distinguishing its effects from other dark energy models, a cosmic game of spot the difference where the stakes couldn't be higher. Whether negative mass particles are real or just a mathematical curiosity, they force us to confront a profound question. Is the universe's expansion driven by something we've overlooked or by something we've yet to imagine? In the hunt for missing energy, sometimes the most radical answers aren't just about finding what's hidden, but daring to reconsider what matter itself could be. Supersymmetry whispers of a hidden cosmic symmetry so perfect, so elegant, it could solve nearly every puzzle in modern physics, if only we could find it. This grand theory, often called SUSY for short, proposes that every known particle has an undiscovered superpartner, a shadowy twin with slightly different properties. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. At ultra-high energies, these twins would be indistinguishable from their ordinary counterparts, their behaviors perfectly mirrored. But as the universe cooled after the Big Bang, this symmetry broke like a frozen pane of glass, shattering into jagged pieces, leaving behind a fractured reality where most superpartners became too massive for us to detect. Yet what if traces of that primordial symmetry linger? What if the energy we've been missing was hiding in the cracks all along? Here's where the magic happens. In a perfectly supersymmetric universe, the contributions of particles and their superpartners to the vacuum energy would cancel out exactly positive and negative terms, balancing to zero. But if supersymmetry is broken, as observations suggest, that cancellation becomes imperfect. Tiny residues of energy could remain, like unpaired socks left behind after laundry day. These leftovers wouldn't match the staggering predictions of quantum field theory's vacuum energy, but they might align with the far smaller yet still mysterious value we attribute to dark energy. Imagine a symphony where every instrument has a counterpart playing in perfect opposition. If just a few musicians are slightly out of tune, the resulting dissonance might be precisely the hum we've mistaken for dark energy's whisper. The beauty of this idea lies in its economy. Supersymmetry wasn't invented to explain dark energy. It emerged independently as a solution to thorny problems like the hierarchy puzzle, why gravity is so weak compared to other forces, and the unification of fundamental interactions. Yet its mathematical structure naturally leaves room for residual vacuum energy when symmetry breaks. Some models even suggest that the lightest supersymmetric particle could be dark matter, while the next lightest decays into the vacuum energy driving cosmic acceleration. One elegant framework, two cosmic mysteries solved, but the universe rarely makes things that simple. Despite decades of searching, particle colliders like the Large Hadron Collider have found no conclusive evidence of superpartners at the energy scales probed so far. This doesn't disprove SUSY. The missing twins might simply be heavier than we'd hoped, their effects more subtle, but it forces theorists to consider uglier versions of the theory where cancellations are less precise and predictions less elegant. The dream of a perfectly balanced cosmos fades, replaced by messier scenarios where supersymmetry's broken remnants only partially account for dark energy's effects. Still, the possibility lingers like a half-remembered melody. Future colliders probing higher energies might yet unveil these shadow particles, or delicate astronomical measurements could reveal patterns in dark energy's distribution that hint at supersymmetric origins. Until then, SUSY remains a tantalizing what if, a reminder that the universe's missing energy might not be lost, but waiting patiently in the wings, dressed in the guise of a particle we've yet to meet. String theory paints a picture of reality far stranger than we ever imagined, not just one universe, but a near-infinite multiverse where the laws of physics shift like sand dunes in the wind. At its core lies the landscape, a mind-bending concept suggesting our cosmos is just one of 10 to the power of 500 possible vacuum states, each with its own unique energy density. That's a 1 followed by 500 zeros, a number so vast it dwarfs every atom in the observable universe. In this cosmic lottery, dark energy's puzzlingly small value stops being a mystery and starts looking like a statistical fluke. We just happen to inhabit a universe where the numbers landed in the narrow range, allowing galaxies, stars, and ultimately us. To grasp how this works, picture a colossal, multi-dimensional mountain range where every valley represents a possible universe with distinct physical constants. Some valleys are steep and deep. Their corresponding universes might collapse instantly or rip apart moments after birth. Others are so flat and expansive that matter can't clump together, leaving behind barren voids. Our universe sits in a Goldilocks valley, shallow enough to permit cosmic acceleration, dark energy, but not so flat that structure formation becomes impossible. The catch: there's nothing special about this particular valley. It's simply the one where life could arise to ponder its own existence, a cosmic version of the entropic principle. Critics argue this smacks of giving up, replacing a solvable puzzle with an unfalsifiable, everything is possible cop-out. But supporters counter that the landscape emerges naturally from string theory's equations. When you account for the myriad ways extra dimensions can curl up and the countless configurations of theoretical fields like the dilaton, an explosion of possible universes becomes inevitable. It's less a contrived multiverse and more a mathematical avalanche no one predicted. The implications rattle the foundations of physics. If dark energy's value is random, searching for a fundamental reason behind it might be futile. Worse still, the landscape suggests most universes are inhospitable wastelands, making our existence staggeringly improbable. Yet here we are, measuring the cosmos's acceleration as if it holds some deep meaning, when it might just be a cosmic roll of the dice. Future telescopes could tilt the scales. If the landscape is real, certain statistical patterns should appear in the universe's large-scale structure or gravitational wave background, subtle fingerprints of a multiverse we'll never see directly. Until then, the string theory landscape remains the ultimate Rorschach test. To some, a profound revelation; to others, a philosophical retreat dressed in fancy math. Either way, it forces us to confront an unsettling possibility that the missing energy isn't missing at all. We've simply been asking the wrong question. While string theory weaves reality from tiny vibrating strings, loop quantum gravity takes a drastically different approach. It suggests spacetime itself is stitched together from discrete, indivisible threads. Imagine the universe not as a smooth, continuous fabric, but as a mesh of interconnected loops, each so small that 1,000,000 billion of them could fit across a single atom. At this unimaginably tiny Planck scale, space isn't infinitely divisible, it's granular, like pixels on a screen. This radical reimagining of spacetime's structure could hold the key to the missing energy problem, not by adding new forces, but by revealing how gravity behaves when the very stage of reality becomes digital. The theory's foundation lies in Einstein's general relativity, which describes gravity as the curvature of spacetime. But loop quantum gravity takes this a step further, proposing that spacetime isn't just bendable, it's woven from quantum-sized loops that link together to form a dynamic network. These loops don't exist in space, they are space. When you zoom in far enough, the smooth geometry we're familiar with dissolves into a frothing sea of interconnected nodes, where distances and volumes can only take certain discrete values. It's as if the universe has a built-in resolution limit, and at the smallest scales, the pixelation of reality becomes visible. This granularity could dramatically alter how energy behaves. In classical physics, energy is smeared continuously across space, but in loop quantum gravity's framework, it's confined to the nodes and links of this cosmic mesh. Just as water molecules in a river can't occupy arbitrary positions but must flow between defined points, energy might redistribute itself in quantized packets along spacetime's underlying structure. Some theorists propose that this could resolve the vacuum energy catastrophe, the infamous mismatch between predicted and observed dark energy, by imposing a natural cutoff on how tightly energy can be packed into small volumes. Think of it like a sponge soaking up water. There's only so much it can hold before it stops absorbing. Loop quantum gravity might act as spacetime sponge, preventing energy densities from reaching the absurd levels predicted by standard quantum field theory. But the implications go even deeper. In this framework, the expansion of the universe isn't just a stretching of space, it's the creation of new spacetime quanta as the cosmic network grows. Dark energy's acceleration could emerge naturally from this process, like how adding more stitches to a knitted scarf makes it longer without needing an external force. The rate of expansion would depend on how these loops interact and entangle, offering a potential explanation for why the universe's growth is speeding up without invoking mysterious dark energy fields. Critics point out that loop quantum gravity remains largely untested, lacking the experimental hooks that make string theories, extra dimensions, or supersymmetric particles, at least hypothetically, verifiable. Yet its mathematical elegance is undeniable, and recent work on loop quantum cosmology has shown it can avoid the Big Bang singularity, replacing it with a big bounce where the universe rebounds from a prior contraction. If spacetime is truly quantized, future experiments probing Planck-scale physics or subtle imprints in the cosmic microwave background might one day reveal its pixelated nature. Whether loop quantum gravity ultimately unlocks the mystery of dark energy or not, it forces a profound shift in perspective. The universe's missing energy might not be hiding in extra dimensions or shadow particles. It could be encoded in the very fabric of spacetime, waiting to be counted one loop at a time. The holographic principle shook physics by suggesting our three-dimensional reality might be a projection, but what if it's also the reason space keeps accelerating? Enter holographic dark energy, a theory that marries the mind-bending idea of a cosmic hologram with the pressing mystery of dark energy. At its core lies a simple but radical premise. The total energy inside any region of space isn't determined by its volume, but by the information capacity of its boundary. It's as if the universe has built-in energy limits, like a computer preventing its processor from overheating by capping power usage. Here's how this solves the dark energy puzzle. In the late 1990s, physicist Raphael Bousso proposed that the holographic principle could constrain vacuum energy, the seething quantum activity in empty space. General relativity lets vacuum energy density be almost anything, but holography imposes strict rules. Just as a movie projector can't display infinite detail on a finite screen, the universe can't pack unlimited energy into a given volume if that energy is fundamentally encoded on its outer surface. Bousso calculated that the maximum allowed energy density scales inversely with the boundary area size. Apply this to our observable universe, and the numbers align suspiciously well with the measured value of dark energy. But holographic dark energy goes further. Unlike the cosmological constant, a static energy baked into space, this framework suggests dark energy evolves as the universe grows. Early on, when the cosmic boundary was smaller, allowed energy density was higher. As expansion increased the boundary's area, the density diluted to today's faint hum. This could explain why dark energy seems so weak now, but might have played a subtler role in cosmic history. Picture blowing up a balloon. As the surface stretches, any image painted on it fades. Similarly, holographic dark energy fades as the universe's screen expands. Critics highlight gaps. If dark energy stems from holographic bounds, why haven't we detected fluctuations as the boundary encodes new information? Supporters point to the cosmic coincidence problem, the puzzling observation that dark energy's dominance began roughly when large-scale structures finished forming. In holographic models, this isn't a coincidence but a natural transition when the universe's scale crossed a critical threshold relative to its information capacity. The implications are staggering. If holographic dark energy is real, the acceleration we measure isn't driven by some alien force. It's the universe respecting its own informational limits, like a dancer adjusting steps to stay within a spotlight's edge. Future tests could look for deviations in the expansion rates, timing, or hunt for quantum entanglement patterns in cosmic voids that mirror boundary dynamics. Whether it holds up or not, this theory forces us to ask, are we hunting for missing energy or misreading the universe's deepest operating manual? What if spacetime isn't the stage of reality, just the play we're watching? Emergent spacetime theory flips centuries of physics on its head by suggesting that what we perceive as the smooth, continuous fabric of the universe might not be fundamental at all. Instead, spacetime could be a collective illusion, emerging from countless quantum interactions like the ripples on a pond's surface arising from countless droplets. This radical idea doesn't just change how we view the cosmos, it could rewrite the rules of energy itself, revealing that the universe's missing energy isn't lost but misunderstood at the most basic level. Think of it like a movie screen. What we experience as three-dimensional space with time flowing forward might actually be a projection, a hologram generated by deeper, more fundamental processes happening beneath the surface. In this framework, particles don't move through spacetime, they create it through their interactions, like fireflies blinking in sync to trace out the shape of a sphere in the dark. If this is true, then energy conservation, one of physics' most sacred principles, might not apply where we think it does. The missing energy could be tied up in the quantum machinery that weaves spacetime together, invisible because we've been measuring the wrong thing all along. The math behind this is as elegant as it is strange. In certain quantum gravity models, spacetime emerges from entanglement, the same spooky connection that links particles across vast distances. Every time two particles become entangled, they don't just share information, they effectively stitch a tiny thread into the fabric of spacetime itself. Scale this up to the universe's countless particles, and you get the four-dimensional continuum we take for granted. But here's the kicker. If spacetime is stitched together this way, then its expansion, what we've been attributing to dark energy, might simply be the natural stretching of this quantum tapestry as new threads are added. No mysterious force required. Supporters point to surprising parallels with condensed matter physics, where emergent phenomena are commonplace. The heat capacity of a metal, for example, isn't determined by individual atoms but by collective vibrations called phonons, quasiparticles that don't exist in isolation, only as patterns in the whole. Similarly, spacetime's properties might not belong to any single quantum interaction but arise from their sum. This perspective could explain why dark energy seems so uniform and weakly interacting. It's not a substance filling space, but a side effect of how space itself crystallizes from underlying quantum chaos. Critics argue this is philosophy dressed as physics, a neat metaphor without experimental teeth. Yet recent work on quantum error-correcting codes, originally developed for quantum computers, has shown startling resemblances to how spacetime might encode information holographically. Even black hole physics hints at emergence, with their entropy scaling not with volume but with surface area, as if the interior were a projection of data stored at the boundary. If spacetime is truly emergent, then dark energy's fingerprint might be hiding in the statistical noise of quantum systems we're already studying. The stakes couldn't be higher. If emergent spacetime is real, then the hunt for missing energy has been looking in the wrong direction. Instead of searching for some elusive particle or field, we might need to probe the very nature of locality and causality, asking not just how energy behaves, but what it even means in a universe where space and time are secondary to something deeper, wilder, and far more profound. What if every particle in our universe has a hidden twin, identical in every way except completely invisible? This isn't science fiction. Mirror matter theory proposes that reality is fundamentally symmetrical, with every electron, quark, and photon matched by a mirror counterpart that interacts with ours only through gravity. These shadow particles would form their own parallel cosmos, identical to ours in structure but forever out of reach, like a ghostly echo vibrating just out of phase. And here's the kicker: this invisible twin universe could be quietly contributing to the missing mass energy we've been desperately searching for. The roots of this idea stretch back to the search for perfect symmetry in physics. Just as a snowflake's left and right sides mirror each other, many equations governing particles work beautifully if you flip certain properties, like swapping left-handed spins for right-handed ones. But nature seems to prefer left-handed neutrinos, breaking this symmetry in ways that still puzzle physicists. Mirror matter restores the balance by proposing that right-handed versions of these particles do exist, they're just hidden in a parallel sector, obeying mirrored laws. Imagine two identical houses sharing a foundation. Residents in one might never see the other, yet both rely on the same ground beneath them. Gravity becomes the cosmic glue between these worlds. While mirror particles wouldn't feel our electromagnetic or nuclear forces, making them undetectable to telescopes or particle colliders, they'd still warp spacetime alongside ordinary matter. A mirror star might pass right through Earth without a trace, yet its gravitational pull would subtly alter the orbits of planets or the rotation of galaxies. This could explain why galaxies spin faster than visible mass accounts for. Their halos might be brimming with mirror matter, invisible yet tugging on stars just like dark matter does. The implications for missing energy are staggering. If mirror particles outnumber ordinary ones, say 5-to-1, their combined gravitational influence could account for dark matter's effects, while their quantum fields might contribute to dark energy's repulsive push. Picture two oceans separated by a thin membrane. Waves in one could press against the barrier, creating pressure that resembles expansion from our side. Even more intriguingly, mirror matter could solve the "why now" puzzle of dark energy's dominance. If the two sectors cooled at slightly different rates after the Big Bang, their energy densities might only recently have aligned to drive cosmic acceleration. Skeptics argue that mirror matter is untestable by definition. If it only interacts via gravity, how could we ever confirm its existence? Yet ingenious experiments are probing the edges of this idea. Sensitive torsion balances search for anomalous gravitational forces at microscopic scales, while studies of neutron stars examine whether their cores might harbor mirror neutrons that alter decay rates. Even cosmic inflation models suggest mirror sectors could have left faint imprints in the gravitational wave background, like whispers from a neighboring room. Whether mirror matter exists or not, it forces a profound shift in perspective. The missing energy haunting our cosmic equations might not be absent. It could be hiding in plain sight, dancing just beyond the veil of our perception, in a universe almost but not quite like our own. Neutrinos are the ghosts of the particle world, passing through planets like they're not even there, their masses so slight we once thought they had none at all. But what if these ethereal particles have been hiding a cosmic secret? A growing body of research suggests neutrinos might not be static, lightweight bystanders in the universe's drama. Instead, their masses could shift over time, undergoing phase transitions that unlock bursts of energy on scales vast enough to drive the cosmos apart. This isn't just tweaking particle physics, it's reimagining neutrinos as cosmic chameleons whose metamorphosis might hold the key to dark energy's grip on the universe. The groundwork for this idea was laid when scientists finally pinned down neutrino masses in the late 20th century. These measurements revealed something peculiar. Neutrinos are absurdly light, at least 1 million times lighter than electrons, yet they outnumber atoms in the universe by billions to one. Even with such tiny individual masses, their collective gravitational pull should leave some mark on cosmic evolution. But here's the twist. Standard models assume neutrino masses are fixed, like immutable labels stamped at the birth of the universe. What if that's wrong? Enter variable mass neutrino theory. Picture a universe where neutrinos start nearly massless in the searing heat of the Big Bang, but as space cools and expands, they undergo a phase transition like water freezing into ice that gradually gives them heft. This shift wouldn't be instantaneous. Just as ice crystals form slowly in a supercooled pond, neutrinos might gain mass in patches and waves across cosmic time. And here's where dark energy enters the story. Every time a neutrino transitions from light to heavy, it releases a tiny puff of latent energy into the vacuum of space. Multiply that by the countless neutrinos permeating every cubic light-year, and you've got a distributed energy source that could mimic dark energy's repulsive push. Critics might argue this sounds like a stretch. How could something as subtle as neutrino mass changes rival the colossal effects of dark energy? The answer lies in the numbers. Neutrinos are so abundant that even minuscule individual contributions add up. Imagine billions of fireflies, each glowing faintly in a vast field. Alone, their light is negligible, but en masse they could outshine a lighthouse. Similarly, if neutrinos release just 1/10,000th of an electron volt during their phase transitions, the cumulative effect across all of cosmic history might be enough to nudge the universe toward accelerated expansion. There's an elegant symmetry to this idea. Just as dark matter's gravitational pull sculpts galaxies, neutrino dark energy could provide the counterbalance, pushing them apart, two sides of the same cosmic coin. Some models even suggest that neutrinos' mass transitions could explain why dark energy seems to have become dominant relatively recently in cosmic terms. If neutrinos spent billions of years in a near massless state before freezing into heavier forms, their energy release would naturally ramp up as the universe aged, matching the observed timeline of accelerating expansion. Experimentalists are already hunting for clues. Projects like the Karlsruhe tritium neutrino experiment are measuring neutrino masses with unprecedented precision, searching for hints of time variation. Others are scouring the cosmic microwave background for statistical anomalies that might betray early neutrino phase transitions. Even the large-scale structure of the universe could hold fingerprints of this process. Subtle clustering patterns in galaxies that reflect epochs when neutrinos suddenly weighed in on cosmic evolution. Yet challenges remain. Current particle physics offers no natural mechanism for neutrino masses to vary across cosmic time, though theories involving extra dimensions or couplings to dark matter fields could provide pathways. And while the math balances on paper, skeptics point out that it's far easier to invoke a cosmological constant than to engineer such a delicate dance of particle metamorphosis. Still, the allure is undeniable, a chance to solve two mysteries at once, linking the quantum oddity of neutrinos to the grandest scale of cosmology. Whether neutrino dark energy ultimately holds up or not, it exemplifies a thrilling shift in how we approach cosmic conundrums. The answers we seek might not lie in undiscovered particles or hidden dimensions, but in re-evaluating the familiar, recognizing that even the most well-studied phenomena might harbor secrets written in the faintest of quantum ink. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, have governed the universe since its birth, but what if we've missed one? Hidden in the vast cosmic ledger might be a fifth force, an invisible hand subtly reshaping the universe on scales so grand it's been masquerading as dark energy all along. Unlike gravity's relentless pull or electromagnetism's binding grip, this proposed force would operate with peculiar rules, weak enough to evade detection in laboratories yet powerful enough to stretch the fabric of space itself across billions of light years. This isn't just wild speculation. Observations of large-scale cosmic structure reveal puzzling patterns, galaxies clustering in ways that defy predictions based on known physics. A fifth force could explain these anomalies by introducing a new interaction that tweaks how matter aggregates over cosmic distances. Imagine a sculptor working alongside gravity, gently nudging galaxies into formations that our standard models can't replicate. This force wouldn't cancel gravity but would dance with it, sometimes opposing, sometimes enhancing its effects depending on the environment. In the voids between galaxy clusters where matter is sparse, this force might dominate, pushing space apart in a way that mimics dark energy's repulsive effect. Theoretical models suggest such a force could arise from exotic particles or fields that interact only with matter under specific conditions. One compelling candidate is the chameleon field, a hypothetical entity that changes its strength based on the surrounding density. In crowded regions like galaxies, the field would weaken, hiding its effects from our instruments. But in the near-empty cosmic voids, it would grow potent, exerting a gentle push that accelerates expansion. It's like a cosmic game of hide and seek, where the rules shift depending on where you look. Critics argue that adding a fifth force complicates physics without sufficient evidence. Yet proponents counter that the universe has never been tidy. Every new force we've discovered was once deemed unnecessary until experiments proved otherwise. The key may lie in future sky surveys, like those planned with the Euclid telescope, which could detect subtle distortions in the distribution of galaxies betraying this hidden interaction. If the fifth force exists, its fingerprints might be etched into the universe's large-scale web, waiting for us to decode them. What makes this idea so tantalizing is its dual promise, solving the dark energy puzzle while opening a window into physics beyond the standard model. Whether it's a chameleon field, a long-range symmetry breaker, or something even stranger, the hunt for a fifth force reminds us that the universe's greatest mysteries might not require inventing new energies, just recognizing that the rules we thought were complete might still have chapters left unwritten. Cosmic strings sound like something straight out of science fiction. Thin, unimaginably dense filaments threading through the universe, leftovers from the first fractions of a second after the Big Bang. These aren't mere theoretical curiosities, they're topological defects, kinks in spacetime itself, formed during phase transitions when the infant universe cooled and its fundamental forces split apart. Picture a pot of boiling water freezing instantaneously. The ice wouldn't form perfectly, trapping bubbles and fractures in its structure. Cosmic strings are the universe's version of those fractures, defects frozen into the fabric of reality, each potentially stretching across billions of light years with the mass of a mountain range compressed into a thread thinner than a proton. Gravitationally, cosmic strings would warp spacetime around them like a taut wire bending a bedsheet. Unlike black holes, which create spherical distortions, strings would produce razor-thin gravitational lenses, splitting the light of background galaxies into identical mirror-image twins. Astronomers have searched for these telltale double quasars or duplicated supernovae, but so far, no definitive string lensing has been found. That doesn't mean they aren't out there. Strings could be drifting between galaxies, too distant or too aligned with our line of sight to reveal their lensing effects. Or perhaps they've decayed over time, unraveling into bursts of high-energy radiation that blend into the cosmic background. But here's where things get interesting for the missing energy puzzle. Even a single cosmic string, if it exists, would carry staggering energy density, enough to subtly alter the expansion rate of the universe in its vicinity. Networks of strings crisscrossing the cosmos could collectively mimic dark energy's effects, not by repulsion, but by introducing gravitational anomalies that skew our measurements of cosmic acceleration. It's like trying to measure the flow of a river while invisible currents tug beneath the surface without accounting for the strings. We might mistake their pull for a mysterious force pushing the riverbanks apart. The math behind this is both elegant and daunting. String energy isn't diluted by the expansion of space like matter or radiation. It scales differently, meaning its influence could persist or even grow over cosmic time. Simulations of string networks show them evolving into complex tangles, with loops breaking off and evaporating in bursts of gravitational waves. These emissions could leave faint imprints in pulsar timing arrays or future space-based detectors, offering indirect proof of strings' existence. Critics argue that cosmic strings, if they ever existed, should have left more obvious traces, distinctive patterns in the cosmic microwave background or more frequent gravitational lensing events. Yet supporters counter that strings might interact weakly with ordinary matter, their gravitational whispers drowned out by louder astrophysical noise. Some models even suggest that strings could have seeded galaxy formation, their immense gravity acting as early cosmic scaffolding. Whether cosmic strings are real or not, their theoretical possibility forces us to confront a deeper question. How much of what we call dark energy is actually the ghostly imprint of the universe's birth defects? The answers might be hiding in plain sight, written in the twisted geometry of spacetime itself, at the far edge of particle physics, where known rules fray into speculation, lies one of the strangest ideas yet unparticles. These hypothetical entities don't behave like ordinary particles with well-defined masses or energies. Instead, they exist in a ghostly state of scale invariance, meaning they look the same no matter how closely you zoom in or out, like a fractal pattern repeating endlessly. Unlike protons or electrons, which occupy specific rungs on the energy ladder, unparticles smear their influence across non-integer steps, blurring the lines between what we consider particle and force. And if they're real, their unique energy signatures could be masquerading as the dark energy we've been chasing all along. The concept emerged from a tantalizing observation. At extremely high energies, certain theories predict that particles might lose their mass entirely, transitioning into scale-invariant states. Imagine shaking a snow globe while the flakes drift and settle at everyday scales. In the violent turbulence just after shaking, their motion becomes scale-free with no characteristic size or rhythm. Unparticles are the cosmic equivalent, behaving more like diffuse clouds of influence than pinpoints of matter. This isn't just mathematical whimsy. In quantum field theory, scale-invariant systems can arise naturally, leaving behind energy contributions that don't neatly match any known particle. Here's where the dark energy connection sparks to life. Because unparticles don't follow the usual energy-mass rules, their pressure-to-density ratio, a key factor in cosmic expansion, could deviate dramatically from ordinary matter. While stars and galaxies have positive pressure and radiation exerts a pushing effect, unparticles might occupy a middle ground, exerting a subtle negative pressure akin to dark energy's repulsive push. Picture a boat gliding on water where the ripples don't fade with distance but linger uniformly, creating a steady pressure against the hull. Unparticles could permeate the cosmos in a similar way, their scale-invariant nature preventing their energy density from diluting as space expands, much like the cosmological constant. Critics argue that unparticle physics borders on the untestable. How do you detect something that doesn't even behave like a conventional particle? Yet supporters point to subtle anomalies in high-energy collisions at particle accelerators, where missing energy signatures or unusual angular distributions of debris might hint at unparticle mediation. Even more compelling are precision astrophysical measurements. If unparticles interact weakly with ordinary matter, their cumulative gravitational effects could subtly alter the cosmic microwave background's polarization or the distribution of galaxy clusters at the largest scales. What makes this idea so electrifying isn't just its potential to explain dark energy, it's the way it challenges our very definition of matter. Unparticles force us to ask, are we missing energy or are we missing the language to describe it? In a universe where the rulebook might still have blank pages, the answers could be hiding in the spaces between the particles we think we know. Gravity feels oddly feeble compared to the other fundamental forces, a fact that's puzzled physicists for decades. A magnet can lift a paperclip against Earth's entire gravitational pull, and a single spark of static electricity can overpower gravity's grip on dust particles. This glaring imbalance might not be a quirk of nature but a clue. What if gravity isn't weaker, just diluted? Enter the radical idea of gravitons, the hypothetical particles carrying gravitational force leaking into hidden extra dimensions, subtly siphoning energy away from our observable universe and forcing us to invent dark energy to fill the gap. The concept builds on string theory's proposal that our universe isn't confined to the familiar 3 dimensions of space and 1 of time. Beyond these could exist compact, curled-up dimensions too tiny to perceive directly, like the grooves on a vinyl record invisible from a distance. Gravitons, unlike photons or electrons, might not be anchored to our 4-dimensional brane of reality. Instead, they could ripple freely into these higher dimensions, their influence diffusing like light passing through frosted glass. The more dimensions they leak into, the thinner their effect becomes in our world, making gravity appear weaker than it truly is. This leakage could rewrite the cosmic energy ledger. If gravitons bleed into extra dimensions, their diminished presence in our universe would require a compensatory energy source to explain the observed strength of spacetime's curvature, an effect we've misinterpreted as dark energy. Picture a hose spraying water into a porous bucket. If half the water trickles out through unseen holes, you'd need to crank up the faucet to keep the bucket full. Similarly, gravity's apparent shortfall might demand an inflated value for dark energy in our equations, masking the truth that we're measuring only a fraction of gravity's true influence. Experimental hints tantalize. In particle colliders, some high-energy collisions show slight energy deficits missing momentum that could hint at particles, including gravitons, escaping into extra dimensions. Meanwhile, precision measurements of gravitational waves might one day reveal anomalies in how their signals attenuate over distance, betraying unseen dimensions siphoning their energy. Even the Large Hadron Collider's next upgrade could probe energy ranges where graviton signatures might flicker into existence before vanishing. Critics highlight a paradox. If extra dimensions exist, why haven't we detected their effects more definitively? Proponents argue that these dimensions could be warped, with gravity's strength dropping off exponentially over microscopic distances, evading current probes. Others suggest that gravitons might only leak into certain regions of the higher dimensional bulk, like water seeping into select cracks in a wall. Whether gravitons are truly escaping or not, the theory forces a profound reconsideration of dark energy's role. The accelerating universe might not need a mysterious repulsive force, just an acknowledgement that the gravity we measure is a shadow of something far grander, stretching beyond the edges of perception. The missing energy could be closer than we think, just a few dimensions away. Einstein's relativity insists that nothing, not even gravity, can outpace light. But what if that's only half the story? Non-local gravity dares to challenge this cosmic speed limit by proposing that gravitational effects can propagate instantaneously across vast distances, untethered by the sluggish crawl of causality. This isn't just a tweak to the rules, it's a full-throated rejection of locality, the principle that objects only influence their immediate surroundings. If gravity can leap across the universe in a blink, the implications for dark energy become as profound as they are bizarre. Picture the universe as a vast network of entangled scales, where the collapse of a star in one galaxy subtly tugs on planets billions of light-years away without waiting for spacetime to carry the message. In this framework, energy isn't strictly bound by the limits of light cones or event horizons. Instead, it's free to redistribute itself non-locally, like a cosmic game of telephone where every participant hears the whisper simultaneously. The gravitational pull we attribute to dark matter's invisible halos, it might not come from hidden mass at all, but from the accumulated non-local tugs of distant structures we can't even see. Here's where the missing energy puzzle takes a sharp turn. If gravity operates non-locally, the apparent acceleration of cosmic expansion could be an illusion, a mirage created by how we've been bookkeeping the universe's energy budget. Normally, we assume gravity's influence diminishes with distance, fading into the background like the echo of a shout. But non-local gravity suggests that every particle, every star, every black hole is perpetually in touch with the rest of the cosmos, their collective gravitational whispers never fully fading. This constant, invisible chatter could mimic the effects of dark energy, as if the universe is self-adjusting its expansion rate through a web of instantaneous connections we've failed to account for. The math behind this is as elegant as it is unsettling. Certain quantum gravity models describe spacetime as a network of entangled relationships rather than a static stage. In this view, what we perceive as gravitational attraction might emerge from quantum correlations that transcend space and time, like a hologram where every pixel contains information about the whole image. These non-local links could effectively hoard energy in ways that defy traditional conservation laws, redistributing it across cosmic horizons faster than light could bridge the gap. The result, a universe where the energy we think is missing has simply slipped into the cracks between local and non-local reality. Critics argue that non-local gravity flirts with paradoxes, violating relativity's core tenet that cause must precede effect. Yet supporters counter that quantum entanglement already demonstrates spooky action at a distance, proving that nature has a way of circumventing classical limits when it suits her. Future tests could look for anomalies in gravitational wave signals or discrepancies in the timing of cosmic events that might betray instantaneous connections. Even the cosmic microwave background's temperature fluctuations could hide statistical fingerprints of non-local influences, subtle patterns that don't quite fit the standard model's expectations. Whether non-local gravity holds up or not, its audacity forces us to confront a humbling possibility. The energy we've been hunting for might not be lurking in some unseen dimension or particle, but woven into the very fabric of causality itself. If gravity can reach across the universe without permission, then the rules of the game and the scoreboard might need a radical rewrite. Imagine the fabric of spacetime not as a smooth, unbroken surface, but as a turbulent quantum seed, constantly churning with microscopic fluctuations so violent they'd make a stormy ocean look placid. This is the realm of holographic noise, where the universe's missing energy might be hiding in plain sight, encoded in the feverish dance of spacetime itself at the smallest possible scales. According to this bold theory, what we perceive as dark energy's gentle push could actually be the collective effect of countless quantum ripples vibrating through reality's foundation, each one no larger than the Planck length, a scale so tiny that a single atom compares to it like the sun to a grain of sand. These aren't ordinary vibrations. At the Planck scale, spacetime isn't continuous, it's pixelated, grainy, like a digital image zoomed in too far. Quantum mechanics tells us that empty space is anything but empty. It's a seething foam of virtual particles popping in and out of existence, warping geometry itself in unpredictable ways. Holographic noise suggests these fluctuations aren't random chaos, but a form of information, bits and bytes of spacetime itself, constantly rewriting the cosmic code. And just as static on a radio distorts signals, this universal static might be subtly altering how we perceive gravity's grip, creating the illusion of an extra repulsive force we've labeled dark energy. The smoking gun for this idea comes from an unlikely place: ultra-precise laser interferometers like those used in gravitational wave detectors. These instruments work by measuring minute changes in the distance between mirrors as spacetime stretches and compresses. In perfect silence, the lasers should trace perfectly straight paths, but researchers have detected anomalies, a faint, inexplicable jitter in the mirrors' positions, as if they're being buffeted by invisible waves. This could be holographic noise in action, Planck-scale spacetime fluctuations manifesting as measurable perturbations. Picture trying to draw a straight line on a sheet of paper while someone gently shakes the table. your line comes out wobbly not because of any error in your hand, but because the canvas itself was trembling beneath you. Why connect this to dark energy? Because the math reveals an astonishing link. When you calculate how much energy these space-time fluctuations would contribute across the entire universe, the numbers align suspiciously well with the observed value of dark energy's repulsive force. It's as if we've been mistaking the hum of quantum static for a mysterious anti-gravity field. The holographic principle adds another layer, suggesting this noise isn't just random, but a projection of deeper processes happening at the universe's boundaries, like ripples on a pond's surface hinting at unseen currents below. Critics argue that Planck's scale effect should be far too weak to influence cosmic expansion. Yet supporters counter that quantum phenomena often scale in counterintuitive ways, the same quirks that allow tiny atomic forces to build mountains over geologic time might let microscopic spacetime jitters accumulate into measurable cosmic acceleration. Future experiments with next-generation interferometers could hunt for distinctive patterns in the noise, spectral signatures that betray its holographic origins. Others suggest studying entangled particle pairs separated over vast distances if their quantum states decohere in ways that can't be explained by local noise. It might point to spacetime itself as the culprit. Whether holographic noise ultimately explains dark energy or not, it forces a profound shift in perspective. The universe's greatest mystery might not stem from some exotic substance or undiscovered force, but from the simple fact that reality, when examined closely enough, is far noisier than we ever imagined. What appears as smooth cosmic expansion on grand scales could be the emergent calm atop a quantum storm, a reminder that sometimes to solve the biggest puzzles, we need to focus on the smallest details. What if the missing energy isn't a cosmic oversight but a system constraint? The simulation hypothesis, often dismissed as sci-fi speculation, offers a startling twist on the dark energy puzzle. Imagine our universe as an unfathomably advanced computer simulation, crafted by beings whose technology operates on principles we can't yet grasp. In this scenario, the energy we've been struggling to account for might not be lost at all. It could represent the computational limits of the hardware running our reality. Every glitch in quantum behavior, every unexplained gap in the cosmic ledger, might simply be artifacts of a system straining to render an entire universe in real time. Think of it like a video game engine allocating resources. Modern games dedicate processing power to render visible objects in high detail, while distant or background elements are simplified to save memory. If our universe operates similarly, the observed acceleration of cosmic expansion, dark energy's calling card, could be the simulation's way of reducing rendering loads at extreme distances. Distant galaxies aren't speeding away because of some repulsive force. The system might be progressively lowering their resolution to conserve processing power, creating the illusion of acceleration from our limited vantage point. This wouldn't just explain dark energy, it could account for quantum indeterminacy, where particles behave unpredictably until observed, like assets only fully rendered when a player looks directly at them. But here's where the debate ignites. If the universe is a simulation, what's the energy budget actually spent on? Physics calculations like gravity, electromagnetism, and nuclear forces require vastly different computational resources than rendering stars, planets, and conscious observers. Some theorists argue that dark energy's uniformity suggests a deliberate optimization strategy, where the simulation sacrifices precision at cosmic scales to maintain fidelity where it matters most, in regions dense with observers. Others counter that a civilization capable of simulating an entire universe wouldn't face such crude resource limits unless we're merely a subroutine in a larger simulation, our reality compressed to save cycles for higher priority processes. The implications verge on philosophical vertigo. If computational constraints shape our physics, the speed of light might not be a fundamental limit, just a buffer preventing data overload. Quantum entanglements, spooky action at distance, could reflect optimized networking protocols, bypassing conventional causality to reduce latency. Even the holographic principle fits neatly into this framework, with the universe's information content scaling to its surface area rather than volume, a common compression technique in computer graphics. Skeptics rightly demand evidence. If we're living in a simulation, where are the glitches? Proponents point to high-energy particle collisions where energy briefly seems to vanish, or quantum measurements that defy classical probability, potential signs of rounding errors in the simulation's code. Some even suggest that precise measurements of cosmic parameters might reveal telltale pixelation in spacetime itself, like finding the universe's frame rate hidden in the cosmic microwave background. Whether the simulation hypothesis holds water or not, it reframes dark energy from a physical mystery into a potential design feature, one that challenges us to consider not just how the universe works, but whether it's working as intended. After all, if reality is code, the answers we seek might not be written in the language of physics, but in the unreadable syntax of the programmer's intent. From Einstein's abandoned cosmological constant to phantom energy's cosmic doomsday, from vibrating higher-dimensional branes to the eerie possibility we're living in someone else's simulation, what unites these 30 theories isn't a single answer, but something far more thrilling: the boundless creativity of science when faced with the unknown. Each idea, no matter how outlandish, represents a daring leap into the darkness, a testament to humanity's refusal to accept "we don't know" as a final answer. Whether you're drawn to the elegance of supersymmetry's hidden particles, the haunting beauty of holographic noise, or the existential vertigo of the simulation hypothesis, one thing's clear: the universe's missing energy isn't just a gap in our equations. It's an invitation to reimagine reality itself. This isn't just about finding the right answer. It's about the wild, wonderful process of exploration, the way every dead end still teaches us something new, every failed theory sharpens the next attempt. When cosmologists tweak gravity's rules or quantum physicists whisper about entangled universes, they're not just solving puzzles, they're rewriting the very definition of what's possible. And that's why this mystery matters. Whether dark energy turns out to be vacuum fluctuations, neutrino phase transitions, or something we haven't even dreamed up yet, the journey to uncover it is reshaping our understanding of everything from the tiniest particles to the fate of the cosmos. So, which explanation resonates with you? The poetic symmetry of mirror matter, the apocalyptic crescendo of phantom energy, or perhaps the humble acknowledgement that we might be missing something fundamental, that the truth could still lie beyond the edges of our current physics? Whatever your favorite theory, one thing's certain: the universe isn't done surprising us. If you've enjoyed this deep dive into cosmology's greatest enigma, hit that subscribe button and ring the notification bell, because the next cosmic revelation could be just one video away. Until then, keep looking up and wondering what's really out there.